we have a solid cylinder disc, wooden disc here, and a hollow ring of aluminum. You see here, they have the same diameter, same size. Okay, can you try guessing which one will accelerate faster, will roll to the bottom first when we put them on the top of the incline and release them at the same time? Which one can you guess that will hit the bottom first?
I don't know.
You think the latter one, right? The empty aluminum ring, because we think that it's lighter and it's easier to accelerate, right?
Yes.
That is our normal sense, normal, what's called instinct. Huh? Let's see it. Okay. He is measuring the speed and the moment inertia of this aluminum disc on the machine. But let's see the, okay, let's see what he talks. He said the term rotational inertia. This rotational inertia is another term of the moment of inertia. Moment of inertia, which is the letter I here. Okay. The same concept with rotational inertia. Is a property of an object that deals with the resistance to the change in state of rotation. We already learned the Newton's second law. Acceleration is force over the mass. The mass here can be understood as the inertia, meaning that inertia with a letter R, meaning that it's resistance to the motion, resistance to motion, to translational motion, which means the heavier, the greater the mass, the harder that you can push it to move, the harder you can accelerate that thing. For example, a giant ship that is too heavy, and therefore it will require a very great force provided by the very powerful engine to make it move, okay, to accelerate it, right? The greater the mass, the greater the inertia, the greater the resistance. That meaning it is more difficult to accelerate it. Similarly, with the I rotational inertia, the formula is angular acceleration is the torque over the moment inertia. So if resist to the rotation, the greater the I moment inertia, the harder to make it rotate and change its rotational velocity. Okay.
Yes.
This is just a concept. With I, he just said that it depends on two things. Depends on the masses of the poise of the components of the object and the distribution of the mass. Distribution, meaning how the mass locates on the object. For example, this is the solid one, solid cylinder. It is different from the hollow one, hollow. The mass distribute only on the outer ring. They intentionally made the two objects having the same mass, m and m, same mass, but a different distribution of the masses, hollow, empty, and solid. Okay, according to the formula, A equal the torque over the moment inertia. Because the mass the same, the torque here is the force times the radius, and the force is the same. That is the component of the weight. They have the same mass, and therefore the weight is the same mg times sine of the angle of the incline, angle alpha. Okay, so same torque but different moment. So I1 result in the angular acceleration alpha 1, and I2 at the bottom result in the second angular acceleration, the same torque. Okay, so when I2 is greater, the acceleration of the second object will be smaller, and therefore it will take longer time to reach the bottom. Let's see which one. Do our prediction, which is the aluminum disc, will hit the bottom first. We see obviously that the wooden one the solid one, huh, rotate faster. The solid one, it rotates faster, meaning that it has the faster acceleration, higher acceleration, huh? Higher acceleration, alpha, meaning it is this one. It has higher acceleration because it has a lower moment inertia, lower I. And it's lower I because the mass is distributed uniformly throughout the object. When for the aluminum ring, the mass only distribute on the outer ring, which is far away from the center. Because it is far, according to the formula, I equal to the integration of the individual distance and infinitesimal mass m. So the mass distribute far away from the center compared to other masses throughout this solid object. Okay, so this ring has the greater moment, greater rotational inertia I, huh? Okay, therefore greater I result in lower acceleration, proving that the moment inertia of this object is 1/2 of m/r squared. Integration, okay. So for this course, we need to do some integration and even some differential equation, as you've seen a few weeks ago, huh? Yeah, okay. Use this formula, this is the definition of moment inertia, r squared times dm. So the point is representing dm here as a function of the radius dm. Okay, the mass m of the cylinder. Let's write the mass of cylinder first is the density times the volume. The volume of the cylinder, is it empty or solid? Yeah, solid, huh? Okay. Cylinder radius r, okay, solid. So the solid cylinder volume is pi times r squared and then times the height. Okay, this is the mass. Density times volume. And the height is big H, huh? Big H here. Even here. Okay. So taking the derivative, dm over dr, we have bringing the number 2 to the front, huh? 2 rho pi r times h, right? So dm can be represented as 2 pi rho h and then times r dr. Now we have the infinitesimal dr. Okay.
Yes.
Now we need to calculate the moment inertia I by r squared dr. dm r squared dm. Now replacing dm in here to this formula, we have r squared times r is r cube, huh? 2 pi rho h. These are the constant, and r cube is a variable, huh? Variable and dr, right? Is it the same here? Yeah, definitely. So all the things in the front, as I said, 2 pi rho h are constant. Therefore, the integration here is r power 4 over 4, huh? Right?
Yes.
And then we need to put in the lower and upper limit. The limit goes from 0 to the radius r, a certain value, a constant, okay? Or we can use the big R, any value R that we want. So this is 0 to R, and therefore putting the limit. So this integration, 0 to R, we have the final result. 2 pi and over 2 is 1/2, okay. 1/2 pi rho h and r power 4. This is the final answer. Yeah, we say, okay, replacing the small r by the big R. Big R, which is any value, a constant, huh? There, this is the solution. This is a solid cylinder. When the height is relatively small, slim, huh? Slim, then this cylinder looks like a wheel. Okay. Yes. So the moment inertia of this cylinder is, we're gonna convert this thing using rho. Okay, calculate rho as well. That density rho 1/2 pi is the total mass over the volume of the cylinder. Total mass. The volume of the cylinder is 4/3 pi. No. Cylinder pi r squared times h, huh? And then times h here. Then times r power 4. Okay. This whole thing is the density. Okay. So we can simplify r 2 power 4 on the top and r square at the bottom. That r square, right? X and x simplify. Pi and pi simplify. So we have 1/2 of the mass and times r square.